So let's say we have a data set and we are trying to do a housing price prediction. Okay, we are trying to do a housing price predictions. We have the size of the house, and based on that, we want to predict what is the price of the house. Okay, so the objective is we want to do a kind of a housing price prediction where based on the price of size of the house and different other features of the house, we want to predict what is the price of the house. This is a price prediction that we are trying to do. Okay, this is how the distribution of my data looks like right now. Everybody can see the screen. So you can see size along the x-axis and price along the y-axis. So you all know the real estate market. There are different types of properties, friends. We have got 1 BHK, 2 BHK, penthouses, duplexes, apartments. And obviously, you can understand that the relationship, uh, the dynamics around the pricing will be very different for different types of houses. If you look at 1 BHK, the dynamics are different. If you look at 2 BHK, the dynamics are different. And if you look at different categories of housing, if you look at different categories of housing, the dynamics will be very different. That is important to keep in mind. Now, we can follow the same approach. Whatever we talked about, we can absolutely solve this in the same way. So we can collect a whole lot of historical data, uh, different types of houses that we have. Like we can look at a whole host of houses from our repository. We know the size, we know the price, and we can absolutely build a regression model, exactly like the way how we discussed so far. We can build a regression model on this data, no problem. Now, the issue is that there are so many different types of houses that if you try to build one single model on the whole data, that model will not be able to give you very good results. Look at the patterns right now. Look at the size versus price dynamics here. So there are a lot of variations you can see, right? Especially if you see the lower end of the spectrum for 1 BHK and smaller houses, it's more of a linear pattern. If you look at the middle segment, 2 BHKs, you see a more of a polynomial pattern. And if you see the segment somewhere in the upper end, the penthouses and 3 apartments, you see a more of a logarithmic pattern. So the patterns are different, right? And on this entire data, if I try to build a single model, let's say if I try to do a single linear regression, it will never work. And this is also applicable for many real world use cases. In the real world, whenever you have some data and you're trying to build a model, going back to the fundamental ideas of supervised learning that we discussed, if you take the entire data and if you try to build a single model on the whole data, they will never work. So you cannot build one single model on the entire data. Okay, so you cannot build one single model on the entire data. That will never work. So how do you go about it? What do you do? What do you do? How do you work it out? So what you need to do now is you need to go and take the whole data, do clustering, divide the data into multiple different groups or clusters. And this is an approach we will learn in the next discussion that is planned for tomorrow. We'll see clustering techniques, K-means clustering, how it is done. But this is the big picture, end-to-end understanding I'm trying to give you, how it's actually done. So you take the entire data and first you do clustering. You try to identify how many groups of data do we have. So from the entire houses data that are there, can we try to identify the different groups and clusters of data? Let's identify that first. What are the different groups and clusters of data we see? So we have small houses, we have medium houses, we have large houses. This is how the distribution looks like for each and every individual category of house. You can see small houses can be represented somewhat like this. Medium houses can be represented somewhat like this. And large houses can be represented somewhat like this. We have basically broken it up. If you see that small houses are basically this part, that's small houses, that's medium houses, and that's large houses. So we have kind of separated it out. Now here I know it's very simplistic. So we are only have a single dimension. So it's very easy to understand what's going on. But in a more real world scenario, we will have multiple features, multiple dimensions, and it won't be as easy to visually see. But the idea should be clear. We take the entire housing data and we try to understand what are the different groups and clusters of houses that we see. That's what we are trying to figure out. And once you understand the different groups and clusters of houses, now you can build separate regression models on each and every group and cluster of house. So you basically have three different data frames right now. You have a data frame separately for the small houses. You have a data frame separately for the medium houses, and you have a data frame separately for the large houses. So now you can look at the you can look at the small houses, and you can build a separate model only for the small houses. You can look at the medium houses, and you can build a model separately for the medium houses. And you can look at the large houses, and you can build a model separately for the large houses. So you can orient your data this way, and you can build models separately for each and every individual group or cluster of house. The small houses build a separate model, medium houses build a separate model, and large houses build a separate model. So you have the individual models now, and this will be much more accurate. This approach will give you much more accurate results than if you had built a single model on the whole data. Okay, if you had taken the entire data here individually, the results would have been, uh, you know, uh, the results would not have been that accurate. Okay, so if you see, if we had taken the entire data here, if we had taken the entire data here and built a single model, we would not have got such an accurate result. But the moment we split our data into different groups, and on each and every group, we are building a separate model, we're getting more accurate results. See how we are able to fit the points a lot more accurately. Okay, so this is the general concept I want to keep in mind. Why are we talking about it? Why are we talking about it now? Why now? The reason is because we are going to be discussing the Mercedes greener manufacturing case study. It's a very, very interesting, very real world data set. So that was the whole objective. I wanted to, kind of show you, how the simple ideas of regression that we covered, how they are used in the real world, in real competition by real companies, and not like a concrete data set. It was a very academic exercise we did, but more like in the real world, how we can relate to it, like a Uber, like the taxi one, like the Mercedes one. So you can, relate to the core ideas better. Okay. So this is also a very, very interesting use case where we are trying to predict how much time it takes to test a car. Okay, so Mercedes cars are highly customized. So customers can literally customize every single aspect of the car that they want. Okay, so you can literally go to an application, a web app, and you can choose from the set of features, and you can order the car, whichever and howsoever set of features you want. You can customize the car in a very detailed manner. Now the important thing is that car needs to be tested. Somebody needs to test the car, right? Many of the things are software oriented. So even in the software, let's say you have a infotainment system, you have a destination navigation system, and you can decide what features you want, what features you don't want. So when the final car is delivered to you, some of those features will be turned off, but it has to be tested. Before Mercedes delivers the car to the customer, they have to exhaustively test the car to make sure all the features are working in tandem. And that is exactly where this use case is. Okay, so this is the use case we can see. But optimizing the speed of their testing systems for so many possible feature combinations is complex and time consuming, because customers can order different types of cars, right? So I mean, if there are so many different types of features that are technically possible, it is very difficult to manually test each of the combinations. So how can we use machine learning to predict how much time a car is going to take to test? That's the whole idea. And these are different types of features that are there. So if I just quickly take you to the solution file, we've actually used a very similar approach here also. So we've grouped the data into different types of cars, and then we have built separate models for each and every type of car. So we followed a very similar approach to what we talked about just a while back, the clustering based approach. Okay. So here also, if you see, there are two notebooks. One is a pure play modeling based approach, and the second notebook is more of a simple exploration, an EDA based approach, where we are trying to explore the data a little bit more in detail. Okay, so I will just very quickly go over it. I will not take you through it in detail, but very quickly go over some of the core concepts. This is my data set. First of all, it's a very real world data set. You can see uh, x0, x1, x2, x3, all the way up to x385. There are total 386 features in a car, and all these have been anonymized. We do not know the exact feature names, because this is again very confidential data, and Mercedes does not want to reveal the exact features of their cars. So each of these columns that you see, they correspond to different types of features in a Mercedes car. So maybe this is like a destination navigation system. Mercedes cars, they have some of the top end models. They have something called destination suggestion. So you can literally sit in the vehicle, you can turn on your car, and the model will look at the historical data and predict where you might want to go next. So it quite literally looks at the time of the day of the week, what time of the day it is, what was your past travel history. Let's say today is a Monday and 9 o'clock I start the car. So the model knows that, hey, I'm going to office, or most likely I'll go to the office because that's what my history suggests. So this is that kind of a feature, let's say as an example. So you've anonymized it. And these values stand for, okay, these are the cases where the feature is not present, and this is the case where the feature is present. So that's how the data actually is like. So each of these are feature names. Imagine this is like another in audio feature. So in all these cases, the audio feature is not present. In all these cars, the audio feature is not present. In this car, the audio feature is present. So you have this is like a binary variable that we have right now. And based on all this, we are trying to predict the y. The y is the testing time. This is the testing time that we need to predict. It's a variable we have to predict. Now, very interesting. If I do a distribution plot on the y variable, you will see a histogram that looks somewhat like this. So we've talked about histograms already some time back, and we understand that histograms are able to show the distribution of my data. So the moment we do the distribution of the y variable, we see a histogram that looks somewhat like this. And if you try to analyze this a little deeply, you will see that the pattern looks somewhat like this. This is what the pattern looks like. So you'll basically end up seeing three broad distributions. Okay, so if you look at the y variable a little bit more in detail, you will broadly see three distributions. Okay, I repeat again, you will broadly see three distributions that are playing out. So these are the three distributions that you will see. Okay, so you'll observe that these are all the cars which are having the testing time. Y is the testing time, right? What is Y? Y is the amount of time it takes to test a car, testing time. So you'll clearly see that. So you'll clearly see that there are a lot of cars which are having the testing time which is average to low. So most likely these are very simple variants of cars. So there are a lot of cars which have testing time which is average to low. There are a lot of cars which have testing times which are around this, and there are a lot of cars which have very high testing time. So very clearly, by looking at this data, we can understand that there are broadly three different groups or clusters of cars. So how many groups or clusters of cars do we see? We are broadly able to see three different groups or clusters of cars. That is the inference we are able to make right now. Okay, so we are able to see three different groups or clusters of cars. Okay, so we've got the cluster one type of cars which are having average to low testing time. We are having the cluster two type of cars which are having mid testing time. And we are having the cluster three type of cars which are having very high testing time. So we are able to kind of segregate cars and create different groups and clusters of cars based on their testing time. That is the inference we are able to make right now. Now, why is it important? Why is it important? Why is it important to do this segregation? Because when we try to eventually build a model, to predict testing time, remember the dynamics will be very different. The dynamics of these cars are very different. If you're looking at cars which are having testing time from 0 to 80, these are very basic cars. They don't have too many features, which is why they are taking very less time to test. These are very like low end models, initial like base models we can call it, right? They don't have too many systems and there's not too much complexity interactions between the systems. So that's why testing these cars is a lot easier. And the models will be very different for these kinds of cars. If you want to build a prediction model, the prediction models for these cars will be very different. But if you talk about the top end cars and the absolute top end luxury cars that we have, like which are taking a lot of time to test, the features are very different. So some of the features present in those top end models are very different. Maybe some of them will have a lot of AI based features, a lot of self-driving, assisted driving features, ADAS, driver assistance systems features you will have, which the base models will not have. And testing those things will take a long time because safety standards are paramount, right? So before you send a car to the customer, you want to be absolutely sure that all these are working, all these systems are working fine. So the moment you're putting in those driver assistance systems, cruise control, lane assist, parking assist systems, automatic parking system, which Mercedes cars have, by the way, all the modern day cars, they have those kinds of basic AI assisted features. And the moment you incorporate those things, it's a very different breed of cars. The dynamics are very different, just like houses, just like the houses example. So we need to build a different model. And I wanted to mention this because next time as we do the exercise, as we see more and more case studies, uh, always try to think from the perspective of building multiple models. So in production also, companies will never have a single model. They will always have multiple models on that they will build on different groups and clusters of data.